Fuzzy matching can recover a misspelled query, but it also creates new mistakes. A Levenshtein threshold sweep shows exactly where typo recall stops being worth the false hits. You'll learn how the pieces fit into a workflow that sweeps typo limits and chooses exact matching, fuzzy fallback, or rejection. I'm Professor Pi, teaching search and IR with simple Python. Imagine you run a small search service for product names or documentation terms. Users mistype queries. Exact lookup is fast and perfect when the key exists, but it fails on typos. Fuzzy matching fills those gaps by asking how close a query is to index terms. The trade-off is clear. Being more forgiving recovers more typos, but it also pulls in wrong matches. That changes user trust and downstream metrics like click rate. A Levenshtein threshold sweep helps you pick the cutoff that balances recall and precision for your data. Put another way, try exact match first, then fall back to distance checks only when needed. Sweep a cutoff from strict to lenient, and watch how many true typos you recover versus how many wrong neighbors slip in. That gives you a policy you can reason about instead of guessing a magic number. For a small catalog, you can test every threshold quickly and see what fits your risk tolerance. We'll build a tiny rule that accepts exact hits, falls back to a Levenshtein check, and refuses ambiguous corrections. The code stays compact and readable, so you can map the idea to your own dataset later. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, show a safe baseline that uses only exact lookup, so we know what we start with. This snippet checks whether a query already exists in a tiny vocabulary. Exact matching is the safest rule when it works, because it returns only keys that are actually present in terms. Here, query is BM26, which looks close to BM25, but is not the same string. The code uses terms.getQuery to make that miss explicit instead of silently guessing. The visible output shows that exact lookup rejects the typo, which gives us a clean baseline before adding fuzziness. Now that we see exact lookup misses the typo, test how close candidates actually are with an edit distance table. This example uses RapidFuzz to measure how close the typo is to each term. Fuzzy search starts by replacing the yes or no exact test with a distance table, and Levenshtein.distance gives the number of single character edits. The dictionary comprehension builds dists, then min selects the candidate with the smallest distance. That gives a plausible correction, but it has not proved the match is safe yet. The output shows the nearest term and its edit count, which is the raw signal we will evaluate instead of trusting blindly. Measuring a single distance is useful, but you need to understand how many terms each cutoff would accept. So, sweep thresholds and summarize what each one keeps. This code sweeps edit distance thresholds and scores what each one keeps. A threshold of 0 behaves like exact matching, so it avoids false positives but misses the typo. As cut increases, kept includes more terms from dists, and the code compares them against gold. Higher thresholds can improve typo recall, but they also admit nearby wrong terms like BM24 or BM250. The printed sweep shows why a fuzzy threshold is a policy choice, not just a typo fix. The sweep also highlights ambiguity. Sometimes the best candidate barely beats the runner-up. Ambiguity is where incorrect corrections sneak in. So, add a gap rule that requires the best candidate to be clearly better. This snippet refuses a fuzzy match when the best candidate is not uniquely better. The earlier threshold sweep showed that cut equals 1 recovers the intended typo, but it also lets in another term at the same distance. Ranked orders candidates by edit distance, and safe requires the best distance to pass the threshold and beat next dist. If the top two candidates tie, the rule returns none rather than pretending the correction is certain. The output shows rejection, which matters because ambiguity is often where permissive fuzzy search creates false positives. Finally, wrap the rules into a tiny evaluated policy that reports precision and typo recall so you can trade off what you care about. This example turns the rule into a tiny evaluated search policy. Decide function first accepts exact matches, then uses RapidFuzz Levenshtein.distance only as a fallback. The fallback still applies the gap rule, so ambiguous typo BM26 can be rejected, while clearer typo BRT can match BERT. The cases list stores the query, the expected term, and whether the query is a typo, which lets the code compute final precision and typo recall separately. The output shows a conservative baseline that keeps accepted matches precise while revealing the typo recall it gives up. If you map this toy example to a real system, think of terms as your product catalog or FAQ index. The same decide function can run as a pre-filter in front of a ranking system, or as a user-facing suggestion layer that offers corrections only when the gap is convincing. On larger catalogs, you will compute distances only for filtered candidates, or use n-gram indexing to keep latency low. Summing up, start with exact match, fall back to a Levenshtein check, and require a clear gap before you accept a fuzzy correction. Use this when typos are common, but wrong corrections are costly. And remember, looser thresholds recover more typos at the expense of false matches, so a winner gap is a cheap safety valve. A useful next step is to tune the gap and cutoff on a real dataset. For example, your product catalog with the most frequent 1,000 search queries and measure precision and typo recall. Try sweeping the Levenshtein cut and the winner gap on that real query log, and pick the point that matches your business metric. If short practical IR helps, subscribe and watch the IR videos.